Alrighty, now that we have this notion of understanding subsets of sets of vectors via the span of a collection of vectors, or how do we take a collection of these vectors and then kind of extend their span, is the best word for it, to define a subset of space? Well, if there are particularly nice subsets of space, we call them subspaces. And what do I mean by quote unquote nice? And here we're going to look at what it takes for a collection of vectors or for a subset defined by a collection of vectors to qualify as a subspace. So let's take a look here. Let me start with a theorem. I would actually like to approach this counterintuitively. I want to start by giving a theorem that's going to serve as a pseudo definition here. So I'm going to refer to a subspace before I actually define it. So here with a theorem, and in parentheses, I'll kind of put pseudo definition. Because in one sense, this theorem meets all the criteria for what it means to be a subspace, but it's not the technical definition that I'm going to use here. So a subset V contained in Rn is a subspace if all of the following conditions hold. The zero vector, which if you're in n-dimensional space, this is just the vector with n zeros in it, right? If this is an element of your subset, if your subset is closed under vector addition. And what I mean by closed under vector addition is, I mean, if you take two vectors, u and v, or let's say u and w in v, then for all vectors u and v, or u and w in v, we have then, or let's make it grammatically correct. For all vectors u and w in v, we have that u plus w is also an element of v. This is what it means to be closed under vector addition. It means if you have two elements of a subset, and for any two elements, if you take their sum, that element is still in the set V, then this is one of the criteria for a subspace. The third criteria is that it is closed under scalar multiplication, which means for every scalar in the reals and for every vector in your subset here, we have that the scaled vector Ku is also an element here. So if these three criteria are held, we're going to call this subset a subspace. And notice this isn't a definition, but it is, right, in a sense. So let's look at some examples of subspaces. Well, one thing you might notice right away is all three of these would hold if every vector in this subset V was just the zero vector. So what if V consisted of one vector, which is the zero vector? Well, it contains the zero vector. If you add 0 to 0, you get 0, which is 0. And if you scale 0 by any number, you still get 0. So this is, in fact, a subspace. And this is called the trivial subspace. Okay. The trivial subspace is trivial, and so we don't talk about it all that much. It won't help us understand a given setting or anything like that. It doesn't provide us very much rich information, but it is important to notice that this is in fact a subspace. Let's look at a more non-trivial example. Let's let L This is going to be the line in R3 passing through the origin with direction vector, we'll call it D, is the vector -5, 1, -4. Let's ask ourselves, is L, which equals, right? If we have a vector passing through the origin, that means the initial vector is the 0 vector, and the direction vector is this vector D here. So the vectors L are going to be vectors, or the vectors, excuse me, the line L can be described as the set of vectors U such that U equals, let's say this is the set of vectors U such that U equals TD for T a real number, right? Because basically what do you have here? Let's look in R3. We have this line, and this won't be accurate. The direction vector won't be geometrically accurate. So kind of suspend your disbelief here for a little bit. And let's imagine that this direction vector D is the vector -5, 1, -4. So humor me and just say, just kind of abstract for a little bit. So we have a direction vector D. This line L is the set of all scalar multiples of this line, right? We've seen lines described this way previously. Now, we're asking ourselves, is this a subspace of, to be more precise, is this a subspace of R3? Well, I don't know. We need to check these properties, right? The theorem answers our question for us, but we need to understand if this applies to the theorem or not, right? So when we look at this set, L, we need to ask ourselves three things. Does the 0 vector live in this set? Well, when T equals 0, we have 0 times the direction vector D, which is 0, right? This implies that the 0 vector is an L. So we're good here, right? We've satisfied the first criteria. We need to see, the next question we need to ask ourselves is this set closed under vector addition? Well, let's say U, we need to check that now, right? So next bullet point, U, let's define this vector to be TD, and then let's have some other vector in this set, let's say SD, right? Because we know every vector in this set is of the form TD here, but we're already using T for the first vector U, and so let's use a different, right? We're scaling it differently for a different vector. So let's call it, let's say it's being scaled by S for T and S in R. Now, how would we check that this is closed under vector addition? Well, let's take the sum of these. What is U plus V? Well, that would be TD plus SD, which is, we know that vector addition is commutative, or excuse me, distributive over, or scalar multiplication is commutative over addition rather, sorry. And so distributive. So that means we have T plus S times D. I have too many properties floating around in my head here. So because we have this distributive property here when scaling vectors, well, now T plus S is still a real number. So this implies that U plus V is an element of this set describing the line. So we're closed under vector addition, which is good. right? Because basically, when we were proving this property, what we just did was we passed, or we knew that vector addition was closed under addition. We knew that it was closed in this set because we knew that vector addition was closed in the real numbers, right? If you take a real number plus a real number, you're not going to get a complex number, right? And so because we knew that it was closed in the real setting, means we were able to prove it for this subset here. What else do we need to check? We also need to check that it's closed under scalar multiplication. So let's say U is again this vector TD here. Well, then we need to let K be a real number, and we need to see what happens when we multiply this vector U by the scalar K. And we want to ask ourselves, is this still an element of our set describing the line, right? Well, let's see. K is the same, or K times U is the same as K times TD. And we know we have a property that scalar multiplication is associative, which means we can group this however we want. And so we can basically pass the parentheses from being TD to first multiplying K times T. Well, and then this is an element in L, since if you ever see the upside, these three dots here, in English, this means since. And if you ever see them the other way, this means therefore. Just some notation for you. But anyway, we have that this is an element of L, since KT is an element of the reals, right? The reals are closed under multiplication. If you multiply two real numbers together, you get something real. And so this means that we're closed under scalar multiplication as well. So now we've shown that this subset L contains the zero vector, it is closed under vector addition, and it is closed under scalar multiplication. Therefore, L contained in R3 is a subspace. Okay, and so these are the checks you have to go through when determining if a given set is a subspace or not. And what you could see here is this direction vector didn't matter, right? After going through the problem, these numbers were extremely arbitrary. Not once did I use these numbers in the proofs of showing these properties. And so what this means is that, and maybe I'll write it over here, any line through the origin in Rn is a subspace, right? And not only was this direction vector arbitrary, really this ambient dimension was arbitrary too. Nothing here in the proof that I've provided here, nothing relied on the fact that we were in dimension 3, right? And so we have this, now we have this knowledge that any line passing through the origin in n-dimensional Euclidean space is necessarily a subspace. And that's a pretty important example. Those are very common in applications. So now we can compactify all of this to give a more precise definition of what it means to be a subspace. So definition, let's let V, capital V here, be the collection of vectors V1 through Vk. So let's say this is a collection of vectors in Rn. V is a subspace if for every scalar A and B in R, and for every vi and vj in the set V here, if for all A, B, and R, and for every two vectors, we have that A vi plus B vj is also in V. And basically what this is saying is if for all of your vectors in the collection here, if for all of these vectors, if pairwise, every linear combination of those vectors is also in the subset, well, then it's actually a subspace, okay? And so this is the definition. And if you'll notice, this really compactifies the conditions into one, right? Because if we have that linear combinations of pairs are always contained in the set, well, then certainly it's closed under addition and certainly it's closed under scalar multiplication, right? And we get to zero trivially. So because, you know, what you could do is you could set up like A vi plus B vj equals 0, right? You could always set this up and then just pick B such that you get A vi equals negative B vj, right? You could always find that. So this is really a succinct way of writing all of our properties of being a subspace here. Now, now we've started understanding subspaces as a collection of vectors. And this is intentional because we have the following theorem. And it's that spans are subspaces. Okay, so if V contained in Rn is a subspace, then there exist vectors v1 through vk, say vectors, such that V is equal to the span of those vectors. So every span defines a subspace, and every subspace can be understood as the span of some collection of vectors. So we can really think about these interchangeably, right? In some contexts, it's more beneficial to consider a spanning set. In some contexts, we don't really care about the individual vectors that span this subset. We just care about the properties of the subset or the subspace in abstract here. And so it's important to note here that we really have this this notion that subspaces and spans can be thought of interchangeably, right? So moreover here, there's a little more for the theorem. Moreover, if W is a subspace for, or excuse me, is a subspace of Rn, and W is contained in V, well, here, let's say we have W as a subspace of Rn, and then every vector, not even the span, but every vector, V1, V2 through Vk, if all of these vectors are contained in W, then we know that V is a subset of W, okay? So if you have a collection of these vectors here, well then, and we're not even talking about the span, right? We're just saying if you have a collection of vectors that span some subspace, when all of those vectors live in some other subspace, then by the transitivity of our set inclusion down there, that we necessarily have that V is a subset of W. Okay. Let's look at a corollary to this theorem. A corollary usually means an immediate result. So like the theorem proves something much more general, but a corollary is something that can be proven basically by reading the theorem and applying it to a specific case. Okay, and so we have a corollary here. This says if V contained in Rn is a subspace, then there exists a set of linearly independent vectors. Let's say V1 through Vk, such that V is equal to the span of V1 through Vk. And again, this is really kind of just applying the first statement of this theorem to the case of Rn, right? It's just saying, okay, if you have a subspace in Rn, you can always find a linearly independent set of vectors that is the spanning set, or that makes up the spanning set of this subspace. Now, what we want to do here is we want to emphasize what happens when you have the span of a set of linearly independent vectors. There's something very special about when you have a subspace that's spanned by linearly independent vectors. We have that these vectors, V1 through Vk, define a basis for the subspace. And this is a very important notion. So I'd like to formally define this. So let's let V contained in Rn be a subspace. The collection of vectors, and usually when you're talking about a basis, you use vowels. So let's go U1 here. U1, U2 through UK is a basis for V if the following hold. Let's say if the following are true. We have that V is the span of this collection, U1 through UK. And this collection, U1 through UK, is linearly independent. So, a basis for a subspace is a collection of linearly independent vectors that span the whole subspace. A basis is a collection of vectors, a collection of linearly independent vectors that spans the entire subspace. A basis is a collection of vectors, a collection of linearly independent vectors that spans the entire subspace. So it is very important, if you have a set of vectors that are linearly independent and they span, and they are the spanning set for, or excuse me, V is the spanning set of those vectors, then that's a basis. Both of those have to be true for your set to be a basis. Let's look at, this notion is pretty important. So let's look at the kind of quintessential example here. Let's look at the standard basis for n-dimensional Euclidean space. Now, let's think in R2 here. At first, here we're in R2. We need a collection of vectors that when you take any linear combination of them, you generate the entire space. Well, That means we need to find vectors x, y, right? We need a linear combination like a1, v1 plus a2, v2, such that v1 and v, like we're looking for these vectors here. Right? We need this to be linearly, and we need these vectors to be linearly independent, meaning you can't write one as a linear combination of the other. And we also need that their collection spans all of the XY plane, right? Well, you can get this pretty easily by the following combination. X10 plus Y 0, 1, right? Certainly, this gives you all vectors x, y, and the domain is R2, right? This lets you have any vector in the XY plane. We call this vector E1. We call this vector E2. The standard basis for R2 is the collection E1, E2. Okay, this would give you a basis. It's very easy to check that these are linearly independent. It's very easy to see that these span the XY plane. What would you do for R3, right? For R3, you would do the same thing. You would want like X, Y, Z. So here I could have, excuse me, I got a little bit ahead of myself. I could draw the vectors. Like here's E1, here's E2, right? They're just vectors of unit length in the coordinate axis directions. So like E1 was in the X direction, E2 was in the Y direction. Here we would have X100 plus Y010 plus Z001, right? And then we would have vectors E1, which is I hat, E2, which is J hat, and then E3, which is K hat, right? That's exactly E1, E2, E3. And so your standard basis for R3 would be, you know, E1, E2, E3. This generalizes, right? If you'd like this picture finished, there's our directions, X, Y, Z. And so the standard basis for Rn is E1, E2 through En, where EI is the vector with zeros in every spot, but the one entry in the ith row. Okay, so it's just like this. E1 has a 1 in the first spot, E2 a 1 in the second, et cetera, et cetera, et cetera, right? Cool. Now let's define, we've seen what a basis is. We've seen kind of the quintessential example here. Let's define the dimension of a subspace. Let's let V be, let's let V be a subspace with basis U1 through UK. And let's say V here is contained in Rn, right? Then V, we say the dimension of V is, and we write this as dim V, and it equals K. It's the number of vectors in your basis, right? This makes sense. When we're in two-dimensional space, we have a basis with 2 elements. When we're in 3-dimensional space, we have a basis with 3 elements, et cetera, et cetera. When you are in a k-dimensional subspace, your basis has k elements, right? So this would be a k-dimensional subspace of n-dimensional space. Right? So, and here we would have that K is necessarily less than or equal to n, right? I mean, you could have a maximum dimensional subspace. For example, like the unit sphere. Well, let's take the unit ball, meaning a sphere with the inside included, right? That's a three-dimensional object sitting inside a three-dimensional space. Here's a definition. The codimension of V is codimension of V, which is given by n minus the dimension of V. Sometimes it's more convenient to talk about the codimension of a subspace. The codimension of a subspace basically gives you how much freedom do you have to move around, like how much freedom do you have to take a subspace and move it around in this ambient space, right? The codimension tells you how many dimensions of freedom you have to move this subspace. And so in a lot of contexts, especially topology, if you're interested in topology, then the codimension is a very important notion as well. So I'm not sure how much we will discuss that in this course per se, but it's worth defining now since we're already defining the dimension. All righty, I think, let's see here. I think what I'm going to do is I'm going to break here. This video might be getting a little lengthy already, and the next video may be a decent amount shorter, but at least there's a break for our attention spans, including mine. So what I'll do next is look at an example of finding a basis for a subspace, and then how to extend a basis from a subspace to a space that's including this subspace. And so we'll look at some examples and these notions. I'll just split this up into a next video here. So.